So now we have completed our chapter on external flows. Okay, we have discussed some of the empirical solutions and some of the analytical solutions, and just with regards to the fluid dynamics applications, like what is the hydrodynamic mechanism behind the reduction of a drag or increase in a drag. We have already discussed those things in detail in your fluid dynamics course. Okay, so I would once again advise you to keep your fluid dynamics course with you, right, and just revise everything from that. Otherwise, the explanation, to a little extent, I have given you some hints about those points, and more explanation you can see in your book as well. Okay, so if you have any question, you are again welcome. Now let's extend the discussion to the internal flows. You already know that those pipes are used for transportation of oil, water and many liquids. So what is the difference between, and we call the flow inside the pipe as an internal flow, right? And what is the technical definition behind these two classifications, the internal flow and external flow? That in internal flow your boundary layer cannot grow infinitely. Okay, and this is the main characteristic of this thing, and based upon this thing, just by the width of the boundary layer we can define few regions inside the pipe. Okay, if you remember, we talked about few applications of the certain types of the cross section in the pipe. Like for example, if you consider a rectangular cross sectional area pipe, you might be seeing those kind of pipes in air conditioning application. You might be seeing those ducts and all that. Why? Because they don't have to bear more pressure drop, more stresses. Okay, this has something to do with the moment of inertia as well. If you revise your structural mechanics course, you may find the reason. And generally for transportation of liquid, because air conditioning application is about transportation of gas, right? And for transportation of liquid, generally we use circular pipes. Okay, and there is another thing that experiments reveal, that circular pipes provide you more heat transfer as well. Okay, so we would see different relations and we would try to find out the physical reasoning behind that as well, but for the time being you can just note it down that there is a specific reason behind using circular pipes for heat transfer application. Okay, now let's come to the point. This is something a very introductory stuff. We can keep discussing it. We have already done it in the previous course on fluid mechanics. Let's talk about the quantification. How can we quantify the flow characteristics? Now the quantify flow characteristics means in convection we are interested in two parameters. One, friction coefficient, the other one is the Nusselt number or the convection coefficient. So these, if you remember from the very introductory lecture on this convection, Cf was a function of and Reynolds number. So we need to find out this one first, that how should we define this Reynolds number. We already know that this is rho Vd over mu, right? Generally for these pipes, diameter of the pipe is the length scale, is the characteristic length, diameter of the pipe. And if you are using a non-circular cross-sectional area pipe, this diameter should be the hydraulic one. You remember? 4P over AC, something like that, right? So where you take the ratio of 4 times the perimeter of any cross-sectional and with the area, cross-sectional area. So this is the hydraulic diameter, and then rho, you already know, we generally consider the incompressible effects We don't consider any kind of change in the density. Same happens to mu as well. Okay. So let's talk about this velocity. This velocity could be the incoming velocity. It can be outgoing velocity. But if you look at the velocity profile, because of the sticking of this layer, the very next layer with the plate or with the pipe wall, this velocity would be 0, right? And this velocity also is 0. But for example, if you just look at this section, there is a mass flow rate coming in. This mass flow rate needs to be constant. Why? Because you cannot store the mass inside this surface, inside this cross section. You have to let it pass through it, right? So these two mass flows should be constant. Just look at the inlet. Let's talk about this inlet. So if this velocity is, let's say, 1, and this velocity is also 1, but as you cross this cross section, as you enter the pipe, this velocity becomes 0. So mass flow rate obviously should decrease down. But can you decrease the mass flow rate? Not at all, right? So to compensate for this decrease, as you move towards the center, this velocity starts increasing. And the same happens to the other half of the pipe. So that is why you can say you have this parabolic kind of velocity profile at any cross section of the pipe, just to keep the mass flow rate same. Okay. And why it is parabolic? We have already derived it. We have got an analytical solution for the circular pipes at least, that this profile is actually parabolic for circular pipes. For circular pipes, we have parabolic velocity profile. Parabolic profile. Okay. Now, what we can do is, you can see that this velocity is changing with respect to r, isn't it? This velocity, if I say that I am talking in terms of cylindrical coordinates, this velocity would be a function of r. Yes, r theta or L, or what should, or r theta or s. Yes, r theta or x, right? Because I am just looking at a two-dimensional configuration, so I would not consider this one. I would say that v is a function of r and x. R is the radius, x is the length. Now you can see that v is surely a function of r, because as you decrease r, velocity changes, right? But what about x? It has a certain relationship with x. We will talk about that later on. But for the time being, I would just say that beyond a certain point in the pipe, this velocity would no more be a function of x. This velocity would only be a function of r. Did you remember something like hydrodynamical entrance region and hydrodynamically developed region? We use that terminology, right? So whenever you talk about hydrodynamical entrance region, which is the basically initial portion of this pipe when the fluid is coming in, this is something which is hydrodynamical entrance region. I'm just trying to remind you. I will talk about those terms in the next slide, but just to make this point very clear, that beyond a certain point, this velocity profile would only be a function of r. Okay. So you cannot specify a local velocity that, okay, I am going to use this velocity to find out this Reynolds number. So what we can do is, we can take the average velocity. We can take the average velocity at any cross-sectional area r, and that too in the hydrodynamically developed region, right? I am not talking about hydrodynamical entrance region, I am talking about the hydrodynamically developed region. Why? Because in hydrodynamically developed region, your velocity profile is no more a function of x. It remains the same for all cross sections. So my point is that this Reynolds number would be calculated based upon the average velocity. How you can find that out? I would remind you of the formula which we used before. So just a reminder, in external flow, the free stream velocity served as the convenient reference velocity for use in computation of the Reynolds number. You remember we talked about that bundle of tubes as well in the last lecture. So that bundle of tube, which is basically a heat exchanger application, which velocity would you use to calculate the Reynolds number? The maximum velocity. You would use the maximum velocity. So in internal flows there is no free stream, so we take average velocity as the alternate. Right, now how can we find that out? Let's say for any cross section, if I just consider any cross section within the pipe, I say that there is a mass flow rate which is going on, and I just assume that throughout this cross section I have a velocity of V average. I just assume it. Okay, so this rho V average into cross sectional area should be equal to the actual mass flow rate, isn't it? This actual mass flow rate is dependent on R, DAC, right? So this is because U is a function of R, you multiply it with rho, you multiply it with, not multiply it, basically you take its integral with respect to AC, a small cross sectional area. And how you can write this AC? AC is equal to what? Pi R square. So what would be DAC? You just take the differential, this would be equal to 2 pi R dr. So you just replace it over there, and I am just talking about this relationship is only for circular pipes. So if you just take this rho AC in the denominator of this term, so V average would be equal to integral rho UR DAC over rho AC. You just integrate it from 0 to R, because most of the time we will be talking about this circular cross sectional area pipe. This would become 2 pi R dr over rho pi R square. This AC is pi R square. So you would come up with this expression, right? So you can see that V average is a function of UR, U of R. So if you know the velocity profile, you can integrate it to find out V average. So you can say it is not that straightforward. The most convenient one was in the external flow, where you just know the free stream velocity. Okay, fine, you find the Reynolds number out of it, no problem at all. Then you come up to the flow over a bundle of tubes, where you need to find out the minimum cross section, minimum area where the fluid has to pass through, and then you find out the maximum velocity through that minimum area, and that maximum velocity should be used for the Reynolds number. But in case of internal flows, you have to calculate the Reynolds number based on what? V average. And for V average, you need to find out what is the velocity profile inside a certain pipe, whether it is square pipe, whether it is a rectangular pipe or circular cross section. You should use that. But this is the most generalized relationship to find out velocity profile inside any pipe. You just need to take care of this DAC thing, right? So this is the average velocity. Just remember this relationship. This is the average velocity for an incompressible flow. Obviously we are not considering any kind of density changes, so this is incompressible flow, and it is dependent on UR only. Now, just like velocity, that pipe should be at certain temperature, or it may be producing some kind of flux. There are two boundary conditions in heat transfer: either you have flux or you have temperature, right? So let's say if the pipe wall has some temperature different from the fluid temperature, obviously there would be some heat transfer. Okay, so if it is a heat transfer, as the fluid moves into the pipe, its temperature would change. Okay, its temperature would change. If the temperature does not change, it means there is no heat transfer, right? So just like we defined V average we have to define mean temperature as well. Average velocity, we talked about the mean velocity. Let's talk about the mean temperature. So this mean temperature, before going on to this point, I would just spell out few of the points. When a fluid is heated or cooled as it flows through a tube or a pipe, the temperature of the fluid at any cross section changes from Ts at the surface of the wall to some maximum or minimum in case of heating at the tube center. Right? In fluid flow, it is convenient to work with an average or mean temperature which remains constant at a cross section. Why? Because in industrial flows, you don't always keep sticking with the mathematical things. You have to find out something very convenient to work with, and generally those are the mean properties. Okay, so generally we talk about this mean flow, but what is the problem? Problem is that if you have this mean temperature, let's say the fluid is entering this pipe at a temperature of Ti, let's say T inlet, and this is going out at a temperature of T exit, and I am just considering this Ti as the average temperature of this whole cross section. This Te is the average temperature at this whole cross section. Now if this is Ts and the pipe has been designed to do heat transfer, so obviously till this exit point, heat transfer should be maintained. This pipe should be used for heat transfer. What does that mean? That this Ts should be different from this Te, isn't it? That's how you can maintain the heat transfer. That's how you can just keep the heat transfer going on throughout the length of the pipe. Okay, so what happens is that this is Tm. It means as you move along the pipe, this Tm also varies. So this Tm would be a function of x. V average was not a function of x. Tm is a function of x. Why? Because as you move along the pipe, this is very important to understand. As you move along the pipe and you have kept a certain length of the pipe just to maintain the heat transfer, if there is no heat transfer, there is no fun of having a certain length of beyond a certain point. Okay, you can reduce the pipe length then. If you are designing a piping system mainly for the heat transfer, you have to make sure that the heat transfer is going on throughout the length of the pipe. Okay, if it is going on, it means this Tm should be a function of x, right? So this is the main difference between mean temperature and mean velocity. Mean velocity, after a certain point, mean velocity would not change. We will talk about that. Similarly, if we talk about mean temperature would change. Why? Because piping systems are designed to maintain the heat transfer till you reach the exit point of the pipe. Right? If there is no heat transfer till the exit point, it means there is no fun of having that extra length of the pipe. Okay, so the value of the mean temperature is determined from the requirement that the conservation of energy principle be satisfied. Obviously, we talked about the mass flow rate. You remember we talked about in the last slide. We talked about this mass flow rate needs to be conserved. Mass needs to be conserved. So it was law of conservation of energy, mass. And now to define the temperature, mean temperature, we can just apply law of conservation of energy on a certain cross section. Now in case of no heating through the wall, no heating means no flux, you have not installed any kind of heater over there. So E dot fluid can be represented as m dot Cp Tm. Tm is a mean temperature at a certain cross section. This should be equal to the energy transfer. Let me read this statement for the convenience. The energy transported by the fluid through a certain cross section in actual flow must be equal to the energy that would be transported through the same cross section if the fluid were at constant temperature. Okay, this fluid, the whole fluid is at a temperature of Tm. Let's assume that, and the energy transfer across this cross section would be equal to this thing. Okay, so I am not going to explain it in detail. If you have any question, you can ask. but we are applying this law of conservation of energy. So because we have T as a function of R, at any certain cross section T would be a function of R, it is being multiplied by Cp, and then we need to integrate it by del m dot, right? By the way, this del m dot, why we consider this del m dot? Because we need to consider this DAC. So this DAC is again a function of R. We can replace this DAC with this thing. Okay. So what you can have is this del m dot can also be written by this thing, this rho u and DAC. This is basically del m dot, right? So this TR is coming from this thing and this Cp remains the same. Now what you can write is this thing. Tm should be equal to Cp T of R U of R 2 pi R dr if you consider the circular cross sectional area pipe, and then you simply consider this V average. Just see, for this m dot on the left hand side we consider V average, this V average, okay, and this m dot is basically rho V average into A, which is the pi R square term, and finally you come up with this expression. You just need to integrate it. So you can see that this Tm is a function of temperature profile and it's a function of velocity profile as well. Okay, so this is not very simple. In case of internal flows, you have to be very careful that for mean temperature, mean velocity was only a function of velocity profile, but mean temperature is a function of not only temperature profile but also velocity profile. Okay, so you can integrate it, but remember that we have used circular cross sectional area pipe for this one, right? So generally for these properties, rho, mu and all those things, you can use this bulk mean fluid temperature, which is basically the arithmetic average of the mean temperature at the inlet and exit. It means if the mean temperature at inlet is TE and mean temperature at the exit is mean temperature at inlet is TI and mean temperature at exit is TE, you need to find out the properties at this value. Okay, and this is known as bulk mean fluid temperature. So remember, all those relations which we are going to study, they use their properties on this temperature. So this is different from the previous film temperature. You remember that? This is different from that thing. So for the time being, we have defined two parameters. One V average, the other one is mean temperature. V average remains the same after a certain point. V average remains the same. It is not going to be a function of X. But Tm should be a function of X. Why? Because you design the pipe to maintain the heat transfer. Otherwise, there is no physical reason of having a pipe length beyond a certain point. So heat transfer remains to be maintainable. And this is the last point where you need to find out at which temperature you should calculate the properties. Now, again, just a reminder of this Reynolds number thing. You calculate Reynolds number based upon these parameters. If you know this V average, you remember we found out this V average in fluid dynamics course. We found out a relationship for a circular cross sectional area pipe in fluid dynamics course. So this V average was equal to this thing, m dot over rho pi d square by 4. Okay, we calculated that. We found out an analytical solution for U of R in case of a circular cross section, and then we integrated that from 0 to R, and we came up with this relationship which finally becomes 4m dot over mu pi d. So for Reynolds number inside a circular pipe or a tube, you have this relationship. For flow through non-circular tubes, you need to calculate this hydraulic diameter. Okay, so this hydraulic diameter is 4AC over P, and if you talk about a channel, by the way, you may have heat transfer from inside the channels as well. So in that case, DH can be considered as 4AB over 2A plus B, where A is kind of the height of that channel and B is the width. So in all of those figures or tables, you may see the relationship for hydraulic diameters. Okay, so you just need to use this appropriate diameter over there and appropriate V average and find out the Reynolds number. But this is not very straightforward. So to find out Reynolds number in case of internal flows is a little tricky, right? Yes, generally you talk about if you have a very small radius as compared to the length, you call it a tube, right? Pipes are of larger diameters. And if you consider a rectangular cross-sectional area pipe, this is generally called a duct, right? So let me explain those hydrodynamic regions, or you remember although we have done that, but just to remind you, this is a pipe, and as it enters the pipe, the fluid enters the pipe, this velocity profile changes. Why? To maintain the mass flow rate. To maintain the mass flow rate. If your velocity decreases at near the wall, it should increase as you come closer to the center, just to keep the mass flow rate same. You cannot store the mass inside a constant cross section or a surface. So the point is, as it enters the pipe, this boundary layer would start developing. You see, from the top and the bottom wall, this boundary layer would start growing, and there would be a point where those two boundary layers would meet each other. So beyond this point where those two boundary layers meet, beyond this point, you have hydrodynamical entrance region. Beyond this point, and at the right of this point where those two boundary layers meet with each other, this is hydrodynamically fully developed region. This is hydrodynamically fully developed region, and if I mathematically write it down, I would say that V only becomes a function of R. V is no more a function of X, and V average is what? It is just a constant thing. Okay. Now, inside this boundary layer, you may found eddies due to the viscous effects. You may found eddies. You might have looked at those eddies. Why? Because you may have turbulent boundary layers dependent on the Reynolds number. But between these two boundary layers, this region is known as irrotational core. Why? Because there would be no eddies at all. This viscous effects could not be felt over there. Okay, if the viscous effects cannot be felt in this region, in this triangular kind of region, so you would call it as irrotational core flow region. Okay. So we are generally concerned with this region, hydrodynamically fully developed region. So whenever you see some relationship, some empirical relationship or some solution, you always generally consider that you are talking about hydrodynamically fully developed region. And generally those pipes are so long that their entrance region is very small. So most of the time we only consider the flow to be hydrodynamically fully developed. Most of the time. And I would show you some relationship regarding the length of that hydrodynamic and entrance length, and you would see that generally people neglect this thing. So this is the point. Remember these two features of the pipe flow. Any question? Yes. Now obviously if you keep the length high, it has to counter more frictional effects, isn't it? If you keep the pipe length large, what it has to go through that length. So you can say that the contact area of the pipe and the fluid at the wall has increased. So if the frictional effects are more, so your pressure drop would also be adjusting itself according to those frictional effects, right? So if the pressure drop is adjusting itself, so obviously it would disturb all the things inside the pipe. It would amend those. Okay. So this is the same thing which you can extend for the thermal boundary layers. Once the fluid enters the pipe at a temperature Ti, for example, it goes on, and this pipe is at a temperature of Ts. Obviously thermal boundary layer would also be developed. Okay, and just like the previous one, the previous boundary layer discussion, the point where those two thermal boundary layers coming from the top and the bottom they meet each other, this region is at the left of this point you have thermal entrance region, and at the right of this point you have thermally fully developed region. Okay, but what is the difference? The difference is that within this region, thermally fully developed region, Tm is still a function of and T is a function of both R and X. So this is the difference. No, mean temperature would not be minimum. It depends whether it would be minimum or maximum. It depends on the situation that you are taking the heat away from the fluid, or you are giving the heat to the fluid, right? So it depends. If the fluid is at a lower temperature than the pipe, so obviously you would have a minimum temperature at what? Center. If the fluid is at higher temperature than the pipe, you would have maximum temperature at the center. Okay, so that is why it is just representing the profile like this. So how we can define this thermally fully developed region? Just like we defined a term V average in case of hydrodynamically fully developed region, and we said that V average is not going to be a function of R or X. We defined a parameter for thermally fully developed region, and that parameter is the region beyond the thermal entrance region in which the dimensionless temperature profile expressed as Ts minus T over Ts minus Tm remains unchanged. So it means you would not say that T average remains unchanged. V average remains unchanged for hydrodynamically fully developed region. T average does not remain unchanged for thermally fully developed region. But what is the parameter which remains unchanged? This non-dimensional parameter, Ts minus T over Ts minus Tm. So this thing, Ts minus T over Ts minus Tm, it would not be a function of X. It would not be a function of X. In what region? Thermally fully developed region, right? So remember that these are very important points to understand. So the region in which the flow is both hydrodynamically and thermally developed, and thus both the velocity and dimensionless temperature profiles remain unchanged, is called fully developed flow. So just to describe this point, let me draw one thing. For example, this is the pipe, and let us say this is how a velocity boundary layer developed. So beyond this point you have what? Hydrodynamically fully developed region. But if you talk about a fluid which is not having Prandtl number equal to 1, or it is having some different temperature, some different properties, this may be the point where you have thermally fully developed region. And beyond this point beyond this point you would have both thermally fully developed and hydrodynamically fully developed region. So generally you would call this region from this point onwards, you would call it as fully developed region. Otherwise you will have to specify what kind of fully developed it is. Do you understand that? Otherwise you would have to define it, whether it is hydrodynamically fully developed or thermally fully developed. Okay, and these things are used in the design of pipes. Be very careful about these things. Okay, so I just wanted to explain that point. Before moving on, I would let me explain one more point regarding those thermally fully developed and sorry, does the what? Okay. Inner smoothness of the pipe, you are talking about the friction? Yes, yes. For example, if you keep the pipe surface rough, it would have more what? Viscous effects. And if you keep the pipe surface very smooth, it does what to the boundary layer? Obviously the viscous effects would be very low. So you can say that velocity boundary layer, its impact on the fluid would be disturbed by the pipe roughness. Okay, because everything is related to the viscous effects. If you are producing more friction, it would have severe effects. Sorry, what do you use? Obviously, whenever you talk about, please remember one thing, that whenever you talk about the choice of a material or choice of a certain system for any engineering application, you would not see its performance only. You have to look at the cost as well, and you have to compromise, right? It is not that simple that okay, fine, I am going to, let's say, buy what? A very highly efficient system, but can you bear its cost? This is a very important question. Okay, so most of the time you have to make a compromise between the cost and the performance. Okay, so again, those pipes which you are talking about, they may be fulfilling the requirements related to the cost. They might not be very efficient in terms of performance. Okay, so my point is I would just mathematically write it down so that you can understand the definition for hydrodynamically fully developed region. This is the mathematical definition for hydrodynamically fully developed region. Do you understand that? That if you take derivative of velocity profile with respect to x inside the hydrodynamically fully developed region, it would be what? 0. So it means u is only a function of r. Okay. Similarly, we can have a mathematical definition for thermally fully developed region as well. For thermally fully developed region, we have to have what? This non-dimensional profile as 0. This non-dimensional profile should be independent of x. Okay. So remember this thing. Now the point is, what would be the behavior of the friction coefficient or convection coefficient in the fully developed region? I told you we are most of the time interested in what region? Fully developed region. Why? Because entrance regions are generally very small and we just disregard the effects of the entrance region. All the correlations, all the studies, all the investigations, most of the time they are concerned with the fully developed region. So a very next question can be, what is the behavior of the friction coefficient or convection coefficient in the fully developed region? How does it behave? Is it a function of x or is it not a function of x? So next question is, how do CF and H behave in the fully developed region? So just remember that definition. Just look at this definition. Look at this definition and tell me whether CF changes with x or not. Why? Because u is not a function of x anymore. If at this cross section you have a certain velocity gradient, you would have the same velocity gradient at the other point, and CF is the function of velocity gradient. So you can say that wall shear stress would not change along the length of the pipe. Wall shear stress would not change inside the fully developed region. So it means if I draw CF or the other friction factor against the length of the pipe, it would just be like this. It should decrease. It should decrease within the hydrodynamical entrance region. It should decrease. Why? Because the boundary layer is expanding, right? And then it remains constant in the fully developed region. So, sorry? You tell me. The velocity what? Yes. Because boundary layer is expanding, so it would have more time to reach the maximum velocity. More gap, you can say. So hydrodynamical fully developed region this is. This region is beyond this point, you have hydrodynamically fully developed region. So CF or friction factor remains constant in that region. Let's talk about H. We need to keep this parameter constant inside the thermally fully developed region, right? Now, what is the definition of H? Did you remember that? How can you find that out? You remember this K partial T by partial R at R is equal to R over Ts minus Tm kind of definition in the last chapter. Obviously, the parameters were changed according to those subscripts were changed according to the flat plate flow, but still you can see that. Now, can you see this thing? Do you remember this one? Where we said that the heat transfer just at the contact surface between the fluid and the pipe, it should be equal to what? Whatever is going on in conduction should be equal to whatever is going on in convection, right? So we came up with this definition through that energy balance. So let me write it down. If I take the derivative of this parameter, why? Because this parameter remains the same for all the cross sections. if I take the parameter, take this parameter independent of x, because this is the definition of the thermally fully developed region, and I consider its derivative with respect to r, just take its derivative with respect to r. Can I write this thing? If Ts remains the same, can I write this thing? It is very easy to understand, and this would not be a function of x. This would not be a function of x. Now, now just see this thing. Is this perimeter a function of x? K remains the same, Ts minus Tm remains the same. Is this a is this something which is a function of x? Not at all. So what do you say about Hx in the thermally fully developed region? It should also be constant, and in this region it should change. It should change as you move along the pipe. So in thermally fully developed region, Hx remains also the constant thing. By the way, I just said that this Ts remains constant. What if this Ts does not remain constant? It would be a function of x. So more appropriately, I can write it down like this, that Ts is a function of x minus Trx over Ts as a function of x, and obviously Tm was also a function of x. If I take its derivative with respect to r, still you expect the same thing. Minus partial t by partial r over Tsx minus Tm. Why? Because I am considering the derivative with respect to r. All the other terms which are a function of x, they would remain the same. We would treat them as if they are constants. So whether Ts remains the same or Ts does not remain the same, it means for both the boundary conditions, for the isothermal pipe surface or for the flux condition on the pipe surface, H would not change in the thermally fully developed region. I hope I made my point clear. Okay, so this needs to be very clear. You should remember that in the hydrodynamically fully developed region, your Cf is not going to change. In thermally fully developed region, your H is not going to change. Okay, so let me move on to the next point, which was about the calculation of the entrance length inside the pipe. So just look at the definition. The book which we are following, it considers this definition: the hydrodynamical entry length. The hydrodynamical entry length is usually taken to be the distance from the tube entrance where the wall shear stress and thus the friction factor reaches within about 2% of the fully developed value. That if the Cf becomes 2% of the fully developed value, you can say that this is the length of the hydrodynamical entrance region. But what is the physics behind that, where those two boundary layers meet with each other? Right? So in laminar flow, the hydrodynamical and thermal entry lengths are approximated as these expressions. Again, these are correlations from experiments. Hydrodynamical entrance region in laminar flow, you have 0.05 Reynolds number into diameter, and then if you talk about the thermal entrance length, it is 0.05 Reynolds number, Prandtl number d, and you can just multiply it with hydrodynamical entrance length into the laminar. So you can say that thermal entrance length is a function of hydrodynamical entrance length. So what happens in case of turbulent flows? In case of turbulent flows, it was observed that thermal entrance length and hydrodynamical entrance length, they remain the same. Generally they most of the time they remain the same, and that value is almost equal to 10d. Okay, so if you look at these things, this is a plot of Nusselt number where you have a subscript T, it means Ts is the same. Where you have H, it means Qs is the same. So these are the values for different Reynolds numbers. As you increase the Reynolds number, all the values increase, right? All the Nusselt numbers increase. Why? Because you are increasing the Reynolds number. And what is the critical Reynolds number in case of internal flows? Generally we take 2000 to 3000. Generally we take that value as the critical Reynolds number. So as you increase the Reynolds number, its value increases. Why? Because you are going towards turbulence. So turbulence enhances heat transfer. So these are, if you look at this dotted line, this dashed line, it would give you this profile by moving along X, and you can see that after a certain point you have constant Nusselt number. Obviously if you have constant H, you have constant Nusselt number. Okay, and for both of those boundary conditions in thermally fully developed region, the values remain the same. They are not going to be different. Those values of the Nusselt number remain the same for both kinds of boundary conditions at a certain Reynolds number. Okay, again this is a very important conclusion, so it can make your life easy. And this value is equal to what? 10d, right? That, sorry, entrance length. The entrance length is equal to what? 10d. It means this length is around 10d. This length, where there is a change in the Nusselt number, this value is taken to be 10d. Okay. So any question? Any question about the entrance region? No question? Okay, so let me shed some light on the temperature profile inside the pipe. How temperature varies, whether it's a mean temperature or the exit temperature or the inlet temperature, how does it vary? So there are two boundary conditions. Those two boundary conditions belong to flux and temperature. Let me write it down. First, I would consider a case where I consider constant flux condition, constant surface heat flux. It means Q dot S is some constant value. What does that mean? That if this is the pipe, fluid is coming from this side, you would have some heat transfer mechanism over there. This Ts may change, but what do these arrows depict? That there is some kind of heating or some kind of cooling happening on the surface of the pipe through Q dot S equals constant condition. Okay. Now, if you remember, can I write this thing, the total heat transfer? I'm not talking about heat flux. I'm just talking about heat transfer rate. Can I write this thing as this one? This is Ti and this is Te. I mean, this temperature at the exit is Te. So I can write down this total heat transfer rate from the inlet to the exit as if a mass flow rate multiplied by Cp, the specific heat, multiplied by the difference in the exit and the inlet temperature. Okay, this is something which is basically total heat transfer inside or taken from the fluid. Okay, so This is what I can write it down. Now, if I say that this is something which is happening due to convection, how can I write down this Q dot? I can write it down as H, although Hx remains same for thermally fully developed region, but I can write it down as this thing, Ts minus, let's say, Tm. Right? These are the two things. So this is the heat which the fluid has acquired in case of heating the fluid, which the fluid has acquired or lost while going through inlet to the exit. This is the heat transfer rate, and this is the heat transfer rate per unit surface area which was happened due to convection. According to law of conservation of energy, these two things remain equal to each other. Why? Because if fluid is at a temperature Ti and the fluid is at a temperature Te, whatever is happening due to what? Inside the pipe, heat transfer mechanism is simply convection. Okay, so you can say that Q dot, because small q dot, let me put it as a subscript Qs, and this has to be per unit area, so I would multiply As with it. So what would you get? Q dot As would be equal to Hx Ts minus Tm. Can you write it like this? No, I'm sorry. Oh. This has to be m dot Cp Te minus Ti. Okay. So the question is, if I know the inlet temperature, I need to know the exit temperature. What would be that? Ti plus Q dot As over m dot Cp. Just look at that. I just keep T exit on one side and put all the terms on the other side. So if you know T inlet, you can find out T exit. Right? This is what you generally require. And this too in case of what? Q dot S equals constant. Okay? You multiply it with As, and by the way, this Te, I have already told you, this Te is what? T mean at exit. This Ti is what? T mean at inlet plus Q dot S As over m dot Cp. Now, if I want to see the temperature profile, just consider it as if it is an equation of a line. Let me write it down as if it is Tm at the exit, Tm at the inlet plus Q dot, and if I just talk about a circular cross sectional area pipe, I can write it down as Px, and P is the perimeter thing. This small p is perimeter. This small p is, so we can write down this As as a product of P into X, right? And if you consider the total area, it would be P into L. Okay, so just see, does it look like an equation of a line where you say this y equals what? Mx plus c. C is the intercept. So intercept at the y-axis, this is Ti, and as you reaches L, so this value is what? It becomes Te. Okay, so this value is Te, and what is the slope? Right? So if I ask you, what would be this thing? Come on, what is that? Isn't it a slope of this line? Why? Because Ti is what? It is the mean temperature at this point. This is the mean temperature at this point. So I am actually plotting what? Tm against x. Okay, so this dTm over dx, which is the slope, this is basically equal to q dot s into perimeter over m dot Cp. Okay, now see, I can also write q dot s. Now this is very important, please try to understand this thing, that this dTm over dx is basically a constant value. It means this mean temperature raises with x, and the relationship is linear, simply linear. Okay, and what is the boundary condition in that case? The boundary condition is constant heat flux. You would see a different behavior when you have a constant surface temperature as the boundary condition. So q dot s can also be written as hx Ts minus Tm. We have seen the variation of Tm with respect to x. We also need to see the variation of Ts with respect to x. Why? Because both of these things are changing. Ts also changes when you have q dot s equals some constant. So I can write Ts as q dot s over hx plus Tm. Isn't it? So if this is the relationship, let me make it more clear. Let me plot it on a bigger screen. Now this is temperature and this is length x. For mean temperature, this is the line where we started from Ti, we went up to like Te at L. Now this is L. So you can say this yellow line is describing the variation of Tm, right? This yellow line is representing the variation of Tm. Now tell me, what would be the behavior of Ts? Just look at this expression and tell me what would be the behavior of Ts. Come on, this Tm is there, and what is this value? It's a constant thing. It's a constant thing. So if I plot Ts, it should go like this, where you find out all the differences at a certain cross section, and this difference would be equal to what? Right? So at all the points, at all the cross sections inside the pipe, for q dot s equals a constant boundary condition, this difference delta T, which means Ts minus Tm, this difference remains the same and its value is equal to q dot s over h. So if I write down this expression dTs over dx, what would you tell me? Just look at this plot and tell me. If I ask you what is the slope of this Ts, this is the line for Ts. Same slope. Yes, this is having the same slope. This is the line for Ts. So if dTm over dx is equal to this thing, so dTs over dx would also be equal to this thing. Why? Because they increases at the same rate. Okay, and for what boundary condition it is happening? Constant flux condition. Okay, so let's talk about the other boundary condition. Sorry? Okay. You are talking about this equation? This equation? Yes, this is not a function of x, but for example, do you have some equation related to this thing? Isn't it? Do you see this thing? You agree? Now the point is, what is this value? It means whatever the plot you have for Tm, it would simply be having an offset in TS. And what is the value of that offset? Now, by just looking at this thing, can I plot like this? So if I can plot like this, at any point, this value remains the same, isn't it? This gap remains to be the same. Why? Because Q dot S over H is same. Now, if it maintains the same gap all along the length of the pipe, what does that mean? They are increasing with the similar fashion, isn't it? Do you agree? So let's move on. Now the second condition is constant surface temperature, where you have Ts is equal to constant. And again, the problem remains the same. We need to find out what is T exit. If you know the value of T inlet, what is the value of T exit? If you have some parameters, some mass flow, let's say some value of H, you need to estimate T exit, okay, beforehand. Now, there are two methods. And those two methods are, one, either you take arithmetic mean temperature difference, or you have logarithmic mean temperature difference. You remember we use that logarithmic mean temperature in flow over tube bank. Do you remember that? We use that definition. So this is the time to prove it. So log mean temperature difference, these are the two temperature profiles which we can use in case of convection inside a pipe for constant surface temperature condition. So if I write down Q dot, I would say that this is equal to HAS delta T average. On average, what is the delta T inside the pipe? I can say that. And by the way, what is this thing? This should be equal to HAS TS minus some parameter from the fluid, minus some temperature value from the fluid. So what should be this temperature value? We should consider the mean temperature, average mean temperature. Why? Because it would also change with respect to X. So I would say that let's take this TM average. Right? Now, how can you write down this delta T average? We need to consider TM average. So there are two ways to calculate that one. Let's put it down using the first approach, which is the arithmetic mean temperature average. This is the arithmetic mean, and this can be written as delta Ti plus delta Te over 2. And how you can write it down? This is Ts minus Ti plus Ts minus Te over 2. I mean, you don't know what is going to be the value of Tm. So what you can do is, you can take the temperature difference at the inlet, then you can take the temperature at the exit, and then you can take their average. You can take the temperature difference at the inlet, you can take the temperature difference at the exit and use their average to find out total delta T. Right? This is one approach. But this approach gives you many errors. Generally, this approach is not correct. It looks very simple, but this approach is not correct. So what you can do is, by the way, this is something where if I just write it down, this is something which comes out to be equal to Ti minus Te. What? Plus what? 2 Ts. Yes, this is plus 2 Ts. Minus Te minus, okay, yes, this is something. So did I write it down correctly? So anyways, we don't get anything out of it. I just wanted to see what is the variation, but I could not get anything out of it. But this is something which is the first approach. You can consider taking the mean arithmetic average, but this would give you a huge error in terms of calculation. So let's move on to the next approach, which is the logarithmic mean temperature. Let me write down one statement. If I just consider a small cross section inside the pipe, small cross sectional area inside a pipe, and I try to find out the Q dot, heat transfer rate, across this cross section, can I write this thing? M dot Cp into dTm, a small variation in the mean temperature. Obviously mean temperature is a function of x. A small variation in the mean temperature multiplied by what? Cp into m dot. So this is Q dot. But why does this Q dot happen? Because of the convective heat transfer. Okay, and that convective heat transfer can be written as H Ts minus Tm dAs. Okay, we can write it down like this. Now, this is something, by the way, this is not divided by, so don't confuse it. This is m dot Cp dTm equals Hts minus Tm into dAs. So what I can write is, can I write this dTm as dTs minus Tm? Can I write it like this? Hassan? Which term needs to be constant? If Ts remains constant, you get this thing out of it, isn't it? Yes or no? Yes. So let me put it this way. I would say that this, instead of this dTm, I would write down dTs minus Tm, and I would take it negative sign on this side, right hand side. I would divide this as Ts minus Tm, and I would say that this becomes H dAs over m dot Cp. This thing, this one, this is dTm, isn't it? Can I write this thing as this one? Ts is a constant. We are considering constant boundary condition, constant temperature boundary condition at the surface. So this is a negative sign as well. Why? Because if you open it, this would become dTs minus plus dTm, isn't it? Minus dTs plus dTm. dTs is what? 0. So simply you can write it this thing. But what is the advantage? You can take this thing into the denominator, and it is just like as if you are considering the integration of this thing. What you can write is integration of 1 over Ts minus Tm dTs minus Tm equals minus integral H, and obviously there would be a perimeter thing, over m dot Cp into dx. And you can move from 0 to L. You can, by the way, this value what should be this value? This value should be, because it is Ts minus Tm, so this should be from Ts minus Ti to Ts minus Te. I mean, you can integrate it. But if we just consider the generalized values, how does it look like? Isn't it 1 over x into dx? What is that 1 over x? Can you write it down as if like this is natural log of Ts minus Tm? and if you plug in the limits, those limits Ts minus Ti over Ts minus Te, so you would write it down as if it is natural log of Ts minus Te over Ts minus Ti, and this would become HAS, because it would P into L, and minus term would be there, m dot Cp. So this is the relationship. And what was the objective? To find out Te. This was our objective. So how can you write it down? If I take exponent of both the sides, this would become Ts minus Te over Ts minus Ti equals exponent of minus HAS over m dot Cp. This is e raised to power something. So Te would become, this is Te, okay, Ts minus Te, let's do it in step just to avoid any error. This would become Ts minus Ti exponent of minus HAS over m dot Cp, and if I write this Te thing over there, so this would be what? Ts minus Ti exponent of minus HAS over m dot Cp. Sorry? Yes. You remember that? We used this one, and I told you we would prove this relationship in the next chapter. Okay? So just see how T exit varies. For example, if this is the mean temperature at exit, and I just write down the general relationship for mean temperature, it would become Ts minus Ti exponent of minus Hpx over m dot Cp. This is the perimeter thing. This is not pressure, this is perimeter. This As is PL, so I would just use Hpx. So this is the generalized relationship for variation of Tm. And if I plot it, it would vary like this. And it is not a linear function. Remember that. It is not a linear function. And this is going to be Ts. By the way, again, a very important thing to understand. Let me draw it more clearly. So, by virtue of that relationship, if I say this is the value of Ts, this is the value of Ts, obviously Tm needs to be lesser than Ts. That's how heat transfer can occur. Okay. So, if I look at the variation, this variation is following this exponential growth. This variation is following this exponential growth. You can go back and check it on MATLAB as well, just by plotting it. So you would see that it would behave just like this. This would be Tm and this would be Ts. And by the way, by the end of the pipe, they would come much closer to each other. Much closer to each other. Okay. And there is a very interesting thing, that generally this parameter HAS over m dot Cp, generally this is represented as NTU. Generally this is represented as NTU. Okay, and this NTU is an abbreviation of number of transfer units. Number of transfer units, right? And this number of transfer units, if you find out its value, NTU for some combination of m dot Cp, HAS over m dot Cp, if you find out its value, and you look at Te as well, there is a small plot given in your book, if you increase TE and you move up to TS, this 100 is kind of TS value. So if you increase to that up to a value of 5, you would have 99.5. Like for example, if your TS is 100, your TE would approach 99.5, where NTU is 5. Okay, the point is, if your NTU is 5, you approach a maximum, you kind of approach the value of TS. But if you even try to increase the pipe length, now my point is, if you increase the pipe length, why? Because if you increase NTU, you increase the pipe length, isn't it? NTU is what? Perimeter into L, right? So M dot perimeter L over, HAS, HPL over M dot CP. If you increase the pipe length to enhance the surface heat transfer, there would be no benefit of that increase in length beyond a certain point. You would just be wasting your resources, right? So you need to make sure that if you are designing a pipe, you should keep NTU around 5. Okay, so this table only describes this table number. I would just give you the table number. This figure is 8-15. It has given all the values. If your surface temperature is 100 degrees centigrade, this T exit would approach 99.5 degrees centigrade, and it means the temperature difference is very small. So even if you go up to an NTU value of 10, you would only be approaching what? 100 degrees centigrade, right? If you keep all other values 1, so it means length, if you keep the length equals to 5 meter, you approach 99.5. Even if you go up to like 10 meter, you are wasting the next 5 meter. You are wasting the resources. Okay, and there is no fun of having that extra length. So this is the point, that you need to be very careful about NTU, and whenever you have a constant surface condition, constant surface temperature condition, you should be looking at NTU value very carefully, and you should be using what? Logarithmic mean temperature difference. Okay. So time is up. We stop at this point, and I would cover the rest of the chapter in the next lecture, inshallah.